Hi folks, today it's the big day for the microcontroller tutorial series. Today we're finally taking a look at the source code that makes our microcontrollers, make our LEDs, blink. It's basically same thing like explaining hello world to somebody new to C programming, except that these programs are a bit more complex. There are a couple things that I just explained that you need them, but not why and what exactly they do, because we have to take a closer look at a number of things in subsequent episodes. But what you should get at this point is some sort of template that you can use for your own little programs, which might make LEDs blink differently. And what I want to do in this case is use the chance to explain what you need, yes, but also take a look at things. What is the same on all microcontrollers? What is specific to different architectures? And basically how to approach writing a microcontroller program anyway. Okay, that's what we're up to. One more thing. The suspense. One more thing to mention. I've done a bit of rework of the makefile, basically renaming file names and targets so they reflect the microcontroller architecture rather than the development board we've used. Simply because in the previous episode we managed to get away from the Arduino Uno and the TIA Launchpad and the Microchip Debug Express boards. And it's one of those things, it doesn't really make much of a difference right now, but in the long run, not cleaning things up like this makes things ever harder to understand. And these sort of legacy issues accumulate over time. They're perfectly obvious to you if you originally involved with these things or with the development of these things from the beginning. But if somebody wants to enter the game at a later point in time, that can make things kind of, well, hard to come to grips with. And we see similar problems when it comes to microcontrollers and the terminology they use, for example, at other times. You'll find the source code and the updated makefile as usual on the forum at www.stepladder-it.com/bivblog/45. Just grab them there. They are once again BSD licensed, so you can use them for your own stuff. It's not like this is really any rocket science anyway. And of course, if you have questions, comments, whatever, that's also the place to come to. One final thing, in case you wonder what happened to the lighting, yes, I changed the lights here, replaced two 800-watt halogen spotlights with 8 10-watt LED spotlights, which apparently don't seem to work too well with my camera right now. We'll see how I get that sorted out when I edit the video, but just in case you wonder. Anyway, so much about building suspense. Let's take a look at the programs. Okay, one more thing to build even more suspense. This is the standard, 6-line, 7-line, 6-line Hello World program that pretty much everybody who's ever learned C actually started with. We need to include standard IO.h, which defines all sorts of macros and function declarations and whatnot. We need a main function that does something, then returns 0, and that's pretty much it. And when it comes to microcontrollers, things get a bit more complicated. Or something like this. And yes, the stuff is heavily commented. Doesn't mean it still fits on a single screen, but, well, can't please everyone all the time, right? Now the first thing I've done, and this is the same on all three architectures, on the PIC to the left, on the Atmel AVR in the middle, and the MSP430 to the right, is I've defined a preprocessor macro blinks, which I set to 7 unless overridden on the command line, which just determines how many times our LEDs blink before they pause. just really useful to test that, because you can override it on the command line, build stuff with a different setting there, and you can check, yeah, okay, everything worked out. The LEDs are blinking now 3 times instead of 7 times, for example. So that's pretty basic, pretty much something anybody using C probably has done before. Nothing exciting, just so you understand what's going on there. And now for the real stuff. Now, instead of using include standard io.h, we include for the PIC a file called pic14/pic16f887.h. If you use a different compiler suite, by the way, the names might be different, especially with the PIC stuff. Here we say it's a microcontroller we use on the PIC14 family, and yes, the PIC16F887 is actually a PIC14 family microcontroller, whereas the PIC18F13K50 is a PIC16 family microcontroller. Talk about that another time. So we actually have to specify the exact microcontroller here when we include that header file. For the Atmel, we just include avr/io.h, and for the MSP430s, MSP430.h. Now, how does that work? With the PIC, no magic involved. But with these Atmel and MSP430 build environments, it works different. Remember, in the makefile, we actually specified using compiler option -mmcu equals whatever, the microcontroller. And the GCC passes this as a preprocessor macro into the program. So these avr/io.h and MSP430.h actually do something very convenient. They use these preprocessor macros to determine which include file to actually include to get all the definitions they need for a specific microcontroller. SDCC doesn't have that feature. We could probably do this somehow by passing something explicitly into SDCC as a preprocessor macro and then build a similar thing ourselves. And we might actually do something like this that works for PIC, Atmel, and MSP430 sometime, maybe. But for now, we just do it the way things are done by the people who originally designed this. Now, next thing we need is we need to wait for time to pass when we blink LEDs. If we blink at full clock speed, we might still be able to see something with an oscilloscope, but since I don't want to assume that you have one, we just have to slow things down to a speed where our eyes can follow, and my camera in case of the videos. And when it comes to the different architectures we have here, there's slightly different ways to do this. On the PIC, what I do is I've defined a function delay, which takes an unsigned long I as an argument, multiplies I with a constant factor that roughly gets us resolution of 1 millisecond per whatever we put into I. We just count down I with this while loop. This isn't nice. This is actually kind of a dangerous way of coding. First off, busy wait is a bad thing to do in pretty much all contexts except when we deal with microcontrollers. Even there, this can be a problem. Second problem, and that's with the PICs here, using an empty while loop like this, there's a good chance that our compiler might actually optimize this out of the way, which is bad, because then things don't wait and we need an oscilloscope again. If we go to the MSP430, it looks just the same, except that there is a predefined, what I guess it's preprocessor macro, which then includes some sort of inline assembler or whatever. It's called __ no operation, NOP, which ensures that the compiler doesn't optimize this entire construct out of the way, which is much more sensible. I haven't found anything like that for the PIC. I probably could have used, maybe should have used something using a single line inline assembler code, but didn't want to make things look scarier than necessary. With the Atmels, things look completely different. And why is that? Because the header files for the Atmel family already take care of things. What we need to do, we need to define a preprocessor constant f_CPU, which is frequency CPU. And if it isn't set to anything on the command line or in the make file, we set that to 16 megahertz, which is the clock speed at which the microcontroller on an Atmel board runs, because it's using an external 16 megahertz quads. Then we just include a special file, util/delay.h, and that gives us a function called _delay_ms, which we see in a moment in action, and that waits for pretty precisely whatever milliseconds we specify. If you think this is something easy to write, take a look at these header files, because this isn't simple, especially not if you want to try to keep things efficient. Well worth a look, but don't be surprised if you find it hard to understand what's actually even going on there. Okay, with that, let's get to the really interesting part. And first off, I'm going to take things out of the way again. Right, what do we need next? Now, microcontrollers generally need to know what clock source to use and all sorts of other things that I don't even really want to mention at this point. And the way microcontrollers handle these is different from architecture to architecture. With the PICs, what we have is a language extension, a non-standard language extension, which you see here. It's unsigned int __at_config1. This is defined in our header file, and this means we have an unsigned int at a specific address, give it a name, and then assign a value. Don't worry where these come from. To be honest, I just found them on Google. I know where to figure out what exactly they mean and what to put in there if I want to change things. But if you want to get started, just go for Google or take these and copy them to your programs and take care of them once everything else is sorted out. That's PIC. With the Atmels, this is managed outside the source code. That means we don't need any non-standard language extensions, which is a good thing, but we have to put things elsewhere, which is kind of annoying. We're going to take a look at these things later on. If you want to find out more about these right now, the keyword to look for is fuse bits. And yes, they are the reason why factory set 80 mega 32.8p is so much slower than something we pulled out of an Arduino board, where it's already configured to use a 16 megahertz external clock quartz rather than an internal 1 megahertz oscillator. With the MSP430s, there is no such thing as fuse bits or config words or whatever. Instead, what the MSP430 people do, we have our main function, and in there we just set things at runtime. What we have to do is disable the watchdog timer, which is enabled by default. If you don't know what your watchdog timer is, don't worry, we get to that at another point. Just put this line at the beginning of your main function and you're pretty much set. Nice thing about this is we can actually do weird things like changing the clock speed at runtime. Disadvantage is that we can do strange things like changing the clock speed unintentionally at runtime. So this has its advantages and disadvantages. Just 3 different ways to do things on 3 different architectures. Beyond that, things look pretty much the same, except that various names are different. If you remember the Debug Express board, it had 8 LEDs, and these 8 LEDs are connected to pins which are grouped into a single GPIO port. They're, at least on the microcontrollers we're using here, they're 8 bits connected to 8 pins joined together to a port. And by default, these GPIO or general purpose I/O pins are initially set as input pins, which makes a lot of sense because there's nothing more, well, unhealthy for a microcontroller than having one microcontroller connected to the other and both having the pins they're connected to each other with set as output ports, and one trying to output high and the other one output a low. And that basically means you short both microcontrollers and you're probably going to get lots of magic smoke very quickly. So the first thing we need to do if you want to blink an LED is we have to tell the microcontrollers which output pins on which output ports to use as output. On the PIC where we had 8 LEDs all connected to one board, basically what we do is we set the variable or whatever exactly this is, doesn't matter, TRISD, that stands for Tri-State D, that's for the GPIO port D, and the tri-state register, well, there are basically 3 states that an output GPIO pin can have. It can be input, it can be output, outputting low, and it can be output, outputting high. So we set all bits to 0, means all these pins are output pins. On the Arduino board, where we only have one LED at pin B5, B is the port and we need pin 5, things get a bit more complicated. If you're comfortably programming C, you may be comfortable with this, but even then, for a lot of stuff people do with C, you don't need this. So I'll give you a quick explanation, and we're going to talk about this a bit more in another episode, because this is sometimes kind of confusing, and there are people frequently trying to do this in a better way, which then introduces some other problems. What we do here is we take a value 1, shift the bits in our bit to by 5 positions. So this 1 shift 5 is 0 0 1 0 0 0 0, if I didn't miscount. And then we OR that onto DDRB. DDRB is basically the same thing as TRISD, Tri-State D for the PIC, except for 2 things. It's named differently, and it assumes that you set the bits for output to 1 rather than to 0. So yeah, this is a bit confusing. Might actually make sense to clean that up somehow with some interesting stuff that takes care of this using some sort of portability layer. We'll see about this. Basically what this means, we set bit number 5 to 1, and that indicates to the microcontroller we're using pin 5 on port B as an output pin. On the TI Launchpad we had 2 LED pins, and names of course are different again. The port is this time called P1, port 1, and we're using bits 0 and 6, and you do it like this. Pretty much the same thing as here, except that we set 2 bits, and yes, using 1 and shifting it to the left by 0 bits doesn't really make that much sense, but it actually makes things frequently more readable. If you want to call this readable at all, that is. Okay, at this point, what we've taken care of was we've configured our microcontrollers to use the proper pins as output pins, and now we just have to output things there. And start with the PIC again. We do an endless loop, goes all the way to here. And we take a short integer I, and we count from blinks down to 0. We set I to blinks. As long as I is non-zero, we continue and decrement it every round. This is probably sort of unusual. You'd normally use something like for I equals 0, I less than blinks, I plus plus. Come on. Does pretty much the same, except that comparing I to 0 frequently is faster or needs less program space than comparing it to a constant or even to another variable. So when it comes to microcontrollers, you frequently see this kind of idiom. Do that the same over here and here, and then just we turn an LED on, wait for 200 milliseconds, roundabout, then turn the LED off, wait for another 200 milliseconds, and after we've done that blink times, we wait for an extended period. And this is the easy part. To turn the LEDs on, we just set all the pins in our port to 1s, and here we set them to 0 again. On the Atmel, we only deal with single bits, so it's this strange bit manipulation idiom again, same as we've done with DDR-B before, except we now use port B, and here it's port D, to output things to a specific port. And we don't use our homegrown delay function, but _delay_ms, which we got from the util/delay.h include file. Switching the LED off, this is looking even a bit more complicated. Once again, we take a 1 in the rightmost bit, shift that by 5 bits to the left, then negate the entire thing, so we have all bits set to 1 except for bit number 5. We AND that over port B, basically means we set bit 5 to 0 and leave everything else untouched, and then delay again, and so on. And big surprise, works just the same on the MSP430, except that this is not port P1 but P1 out, and we have to deal with 2 bits we want to operate on, so this looks a little bit more complicated. Other than that, it's pretty much all the same. You see, this isn't rocket science. Basically, all you need to know is how to generally approach this, use this as a template, what the input and output and direction register things are named on your particular platform, and that's it. Not much of a surprise here. So at this point, I suggest you grab the sources again at www.stepladder-it.com/bivblog/45. They're there for you. Play around with them. Make the LEDs blink in all sorts of ways you can come up with, just to get comfortable with things. And yeah, that's pretty much all there is for today. Next episode, I'll take a look at these funny bit manipulation things and different ways to do these, and why you might want to do things differently, and why you might not want to do things differently than this. And after that, I think, since we take care of output, we might then talk about input. But that's yet another episode. So grab the sources, play around with things. If you have questions, come there to the forum and enjoy. You're now officially licensed to play around with these things if you like. Good. And other than that, hope you enjoyed it. If you did, let me know. If you didn't, let me know as well. And hopefully see you again soon. Bye.